So hello and welcome everyone to this next video as part of 100 Days to CAT program. Today we'll be looking at the topic of geometry already. Or geometry again. We have already looked at a couple of videos of geometry and now we are going to be looking at a third video. In this video also, I'm not going to be practicing questions of geometry because I think that unlike the remaining topics of quant that you have, geometry is not a topic where I can actually show you different types of questions because there are so many different concepts and theorems and formula that the number of questions are probably 300, 400, and it does not make sense solving 3 or 4 questions. Right? Rather, I'm going to take the opportunity in this particular video to discuss a very basic thing about geometry, which several people actually tend to ignore, right? Which is how to think. Right? How to think about the questions and of geometry, how to think about formulating the solutions for a question in the topic of geometry, and how to come up with solutions. I know that several of you feel that geometry is a difficult topic, and unlike other trainers, I'm not going to disagree. I'm going to agree with you that geometry is one of the tougher topics inside the paper that we have. There are several reasons behind this. One of the most important reasons I feel is that since geometry has got so many different theorems and formula, and if we do not indulge ourselves in the practice of geometry, if we don't submit to it wholeheartedly, then we will not be able to solve the questions of geometry very easily. Because it is not just about remembering theorems and formula, it is also about knowing which theorem and which formula needs to be applied to what question to get to what answer. So to understand this process, that how do we know which theorem needs to be applied where, which concept needs to be applied where, which formula needs to be applied where, and what theorem can give me what kind of an answer, is what this particular video is all going to be about. I'm going to be discussing what thought process and mentality goes into solving a problem of geometry. So before we get into the video itself, I'll tell you that the prerequisites to have any kind of benefit from this video are two different things. First is knowledge of the basics. What basics am I talking about? I'm talking about at least the basics that I have discussed already in the first 2 videos of geometry that we have posted already. Right? There are geometry basics 1, geometry basics 2, in which I've discussed the basics of straight lines, triangles, quadrilaterals, circles, and polygons in mensuration. So mensuration, I don't think you need any kind of a recollection because in school we have tackled mensuration problems the most. But the remaining topics is basic concepts and formula. I've discussed in 2 videos before this. If you have not watched that, I would encourage you to watch that, and I would encourage you to make notes out of that. And those are the basics that we need to know before we even start getting something out of this particular session. Right? Second thing, that should have happened by now anyway, because it's quite late into our preparation, right? So I would expect all of you who are present here or watching this video to have practiced at least 100 questions in geometry across different difficulty levels. So if you have not practiced questions of geometry, if you have just looked at the basic concepts and marked them up, then this video again is not going to be helpful to you. Because only when you have solved 100 questions will you start seeing a kind of a pattern that how are questions solved, what concepts is applied where, is something that solving of questions will give you. Right? So this video is going to be at a slightly advanced level of preparation, that at this point of time, if I come across a question in a mock, I'm still not being able to solve the question of geometry despite having practiced 100 questions. So what is going wrong? This is a general question that students have, and that is what I'm going to kind of tackle in this video. Right? So what should be my approach? If I come across a question of geometry inside my mock, then what should I be thinking about? What should be my approach to get to the solution of this question, right? So the first thing that we have to do, of course, is visualize, right? Visualize. This step is especially important if the figure is not given to you in the question itself, which means as soon as you finish reading the question, you will have to draw the figure. You'll have to visualize exactly what figure is being described there. This particular aspect of difficulty is put several times in the mensuration questions, when they only describe what kind of surface area, what kind of volume you're supposed to calculate, and then you have to visualize how that area and how that volume is going to look like. It is also going to be applicable to any other question of geometry in which there is no figure for sure. Several times, even when there is a figure which is present inside the question, even then visualization becomes important, because it is important for us to separate the figure out into its constituent parts and visualize what all geometric features are present inside. So there is a circle, there is a triangle, there's a straight line, there are quadrilaterals, there's a polygon, all of these are present inside the figure. Then I need to be able to separate them out and then say that, okay, this geometric figure is present, this aspect of geometric, say, concept or theory is present inside the figure. So I need to pick the figure apart and be able to visualize its constituent parts also separately. So visualization becomes an extremely important part of solving the question, and that's the first thing that you have to do in solving any of the questions. Right? Second step, which is in my opinion the most important step towards solution of a question, is association. Right? I've been telling you in this video from the very beginning that just marking up the formula and theorems and concepts is not going to help you solve questions. Why? Because I need to be able to understand that which concept needs to be applied where. So association between what has been given, what has been asked, which particular concept or theorem is going to be fit in to this particular fact that has been given, into this particular aspect which has been asked. So that sense of association needs to be developed, and that is what I have to do. That is that as soon as I read the question and I visualize the figure, I need to ask myself that what all concepts and theorems are associated with the figure which is present in front of me. Right? So first I have to look at the figure and I have to first list down inside my head that, okay, in this figure, because I have a right angle triangle, so I can apply half into basic to find directly for area of the triangle. I can apply the Pythagoras theorem. So these two concepts I'm directly associating with the figure. So the figure itself will tell me a couple of theorems or concepts or formula which are very closely related to the figure. So those I have to list out. Next, what I have to do is I have to look at what's been given. Right? For example, if I look at a figure and there are like 15-20 concepts which I can immediately associate with the figure. Right? But when I look at the given data, the entirety of the given data is all about different angles in the figure. No side lengths have been given, no ratios have been given. Then what I can do is that immediately, as soon as I associate those 15-20 concepts, I can eliminate all the concepts which are not dealing with angles. And because angles have been given, so I will have to focus on what has been given, and then I will have to further filter down whatever concepts in my head were associated with the figure. And then finally, I will look at what's been asked. What is it that I'm supposed to get to? So what kind of result am I supposed to achieve? Is it a ratio? Is it an angle? Is it a length? Again, what type of data am I being expected to produce as the output of the question? That is also going to tell me that which concepts that I've listed down inside my head is relevant to the question that is being asked. Right? So this is what I have to do. First, in my head, as soon as I see the figure, all the concepts associated with the figure should immediately flash across my head and they should form a bullet point wise list. Then this list is going to get further filtered down when I look at what's been given. And then that list is going to get further filtered down when I look at what has exactly been asked. So at the end, probably I'll have 4 or 5 different concepts which I feel might be relevant to the solution of this question. So then what do? Then I take these 4 or 5 concepts and I apply to them. And instinctively, you will know in what order or in what sequence you have to apply them. And as you apply them, you will get better clarity on what all results you're getting out of them and what is sufficient, which all concepts are sufficient for you to get to the answer of the question. So this should be the approach whenever I'm solving a question inside a mock or the actual CAT paper, or even while practicing. In fact, while practicing, say, suppose you are solving really difficult questions, you are, say, taking up questions from level of difficulty 3 or 4 or expert level questions or advanced level questions of geometry, and you are finding that 5-6 questions in a row you are not being able to get to the solution of. That is absolutely fine. That is okay for you, for it to happen, because as I said, geometry is not an easy topic. But what we can ensure is that with this association, if I figure out, suppose that there are 3 concepts which are basically going to be related to all of these 3: figure, given data, and data what has been asked, right? And if the solution also uses those very 3 concepts to get to the answer of the question, that means that I am getting better at geometry. So whatever concepts I'm thinking of, whether that is the same concept which is being applied to the solution of a difficult question, that means that my association is getting better and my capability of solving geometry questions is also getting slowly better. If there was some concept inside the solution which I did not even think of, then that means that I'm a bit rusty in questions which require that particular concept to get to the answer. So then I will have to make a mental note of that concept, that, oh, okay, when this figure is given, when this kind of a data is given, when this is the data which has been asked, then I should also think about this particular theorem which can be applied to get to the correct answer. So this association is, of course, the most important step in the approach to solving geometry questions. And finally, of course, once you have listed down all the concepts in your head which you think might be associated with figure, given and asked, then you apply them and you'll get to the answer. Right? Application is the easiest part. Right? But what to apply, when to apply, that is what we are supposed to develop when we look at the figure. Let me give you an example of say what I'm talking about. Okay, so suppose if this figure is given inside the question, I'm not even going to be looking at what's been given and what's been asked. I'm going to talk about what all concepts you can list down when you look at this figure immediately. Right? You can see a triangle ABC, in which DE is a straight line which is perpendicular to AB. Another straight line from C on AB is parallel to ED. The name of the straight line has not been given. Let me name it as F, right? CF. So these are the things that have been given. As soon as I look at this figure, what all concepts can I immediately think of? I've also been given the length of AD and BD, right? So first thing that I'll think of is the Pythagoras theorem, of course, right? It's a right angle triangle, so we can apply the Pythagoras theorem. So right angle triangle Pythagoras theorem will, of course, come hand in hand. Area of triangle concepts. So when I say area of triangle concepts, I mean there's a right angle triangle, so you can apply half into base into height. Also, here you can also find out the ratio of the areas of different triangles. For example, if I draw a straight line from D, and pardon my drawing here, okay, I'm doing it without a scale, to C, right, then I can say that area of triangle BDC and area of triangle ADE, or rather area of triangle BDC and area of triangle ADC are in the ratio of 3:2, right? Because BD and AD are 3 and 2 lengths respectively. So I can probably use the ratio of the lengths of BD and AD to find out ratio of the areas of different triangles inside this figure as well. So that is also some concept that I can apply. What else? I can apply similar triangles. Of course, I can definitely apply similar triangles in this figure because we have got parallel lines, and parallel lines inside a triangle means that two triangles will be similar. For example, in this question, of course, angle ADE and angle AFC will be equal because corresponding angles, and similarly angle AEC, sorry, angle AED and angle ACF will be equal. So triangle ADE and triangle AFC will be similar. So all properties of similar triangles can be applied to this question. Then we have got parallel lines and transfers. So of course, parallel line and transfer system, angle-based concept we can apply. Corresponding angles are equal, alternate angles are equal, interior adjacent angles are supplementary. All of these can be applied. Then we can also apply triangle-based angle concepts. That sum of the angles of a triangle is 180. Exterior angle is equal to sum of interior opposite angles. Those concepts can be applied. And because we have a right angle triangle, so trigonometry can be applied because sine, cos, tan, all trigonometric ratios are defined for right angle triangles. And finally, we can also apply mass balance theory probably here because we know that D is dividing AB in the ratio of 2:3. And what is mass balance theory? I would encourage all of you to check out that video. It's on our channel. I will do one thing. I'll put the link of the video in my description. Mass balance theory is a very interesting, small, very simple concept that can be applied to find out ratio of the lengths into which a point divides a straight line. And those can be very useful in triangles and quadrilateral questions. Right? So as soon as I see this figure, even without looking at the text of the question and what has been given and what has been asked, these concepts should immediately come up in my head in front of me, right? I should immediately be able to visualize the fact that these concepts can be applied. Then based on the text of the question, what kind of data has been given, what has been asked, I can filter this down, the list of these concepts down, and then I will be left with 2 or 3 concepts which I can then apply and get to the correct answer. So this is how we think about geometry questions. So now what I'm going to do is that I'm going to show you a couple of figures and let you do the same thing on your end. Right? Next figure I'm going to show you, and I'm going to give you, say, a minute. Right? So take a minute and list down every concept that you think can be applied to this particular figure. And at the end of a minute, I will then show you my list and what all concepts came across my head. So you can see that whether the concepts that you are thinking of and the concepts that I'm coming up with are similar or not. Okay, so that's the end of a minute. Right now, let's see what all concepts I came up with. Maybe you have come up with more, but I'll tell you what all things I thought about when I looked at this particular question, right? Or this particular figure. First thing that I thought of is secant section theorem, right? I've got PD a tangent and PB a secant, which are both meeting at a point P. So which means I can apply the secant section theorem here. PB square is equal to PB into PA. What else? I can apply alternate segment theorem, because I have a chord BD and a tangent PD creating an angle BDP at the point of contact. So this angle will be equal to this angle. I can apply alternate segment theorem. What else? I can of course apply semicircle concepts. So when I say semicircle concepts, I know angle in a semicircle is 90 degree, which means that angle ADB is a 90-degree angle. So as soon as I know that this is an angle in a semicircle and it's equal to 90 degree, I know it's a right angle triangle. We can apply Pythagoras theorem. We can apply half into base into height for the area of this triangle. We can also apply the concepts of trigonometry. Right? So right angle triangle concepts along with that. What else? I can apply similar triangles concepts also here. How? Because clearly if I look at triangle PDB and PDA, I've got one angle equal, angle D and angle A are equal, and angle P is common to both of them. So which means that triangle PDB and triangle PDA are similar to each other. That is also something that I could figure out as soon as I looked at this figure for a bit. Then probably I can make some constructions because it's a circle. So looking at a bit more obscure kind of concepts, if I say draw here a second angle in a semicircle, I can probably create a cyclic quadrilateral. Maybe cyclic quadrilateral concepts can be applied if at all the question demands something like this. And of course, I can apply angles in triangles concept, which means some of the angles of a triangle is 180. We have got exterior angles, we have got interior angles. So all of those can be applied as well. And finally, the circle is circumscribing triangle ABD, which means it's a circumcircle, which means circumcircle based concepts. That distance of the circumcenter from the three sides or three vertices of a triangle are equal. I can use the circumcircle concepts and properties to figure out the circumradius of this triangle. So all of those also I can apply. If you have listed down these concepts and more, then you have thought properly about this figure. So this is what we are supposed to do. This is what I'm supposed to practice whenever I'm practicing geometry questions. I need to look at the figure and I need to jot down inside my head what all concepts can be applied to this and then look at the questions. When you practice geometry like this, your capability of understanding which concept needs to be applied where will become better slowly and steadily for sure. Okay. And this needs to happen very, very consistently. Not once or twice, but every time that you see a figure, a geometric shape, you need to simply quickly ask yourself what all concepts can be applied to a figure. For example, let's do one more figure here. Right? So let's look at this particular figure, which is of course the Deathly Hallows sigil from Harry Potter. Right? So I'm talking about regular day-to-day figures like these. So again, take a minute and again list down whatever concepts you can think of with respect to this figure. And then after a minute, I will discuss what all things comes to my mind as soon as you see this particular figure. Okay, so that was a minute. Let me discuss what all things I can think of when I say look at the Deathly Hallows sigil. Of course, the straight line looks like the altitude, looks like the median, looks like the angle bisector as well, which means the triangle is an equilateral triangle. The circle inside, which is a ring of a resurrection, is your incircle of the triangle, of the invisibility cloak, right? And because this is also an altitude inside an equilateral triangle, so which means there will be a 90-degree angle which is present between the elder wand and the cloak of invisibility. So which means you can apply the Pythagoras theorem. It's a median, so you can apply the Apollonius theorem. You can find out ratio of areas as well, right? Because I know that the center of this circle will also be the centroid. So I know it will be a 2:1 ratio division of the elder wand. So which means that if I draw a straight line like this, then this straight line will divide this half of the invisibility cloak triangle in the ratio of the area of 1:2. So ratio of areas of different parts of this figure you can find out. And of course, because that's a 90-degree angle, you can apply trigonometric concepts as well. These are the things that I came up with. If there is more that you have come up with, then great. But what I'm trying to point out here is that in regular, everyday, day-to-day shapes as well, when you start figuring out that, okay, there is geometric concept, this that can be applied here, there is that geometric concept that can be applied here, then you are getting better at geometry. Right? Let's do one more of these regular shapes from our day-to-day lives. Let's look at America. I'll give you 30 seconds. Right? 30 seconds, list down or write down whatever concepts that you can think of, and after 30 seconds, I'll show you what all I thought of. Right. So that was 30 odd seconds. Not many concepts that I could think of. Maybe you could think of more, but the first thing that I think all of us should have thought of in this figure is concentric circles, right? There are 1, 2, 3, 4 concentric circles, and their radius appear to be in an AP, right? Thickness of all these concentric circles or distance between all the concentric circles seem to be equal. So this is X, this is X, this is X. So the radius of the first one is R. Second circle will be R plus X. Third circle will be R plus 2X. Fourth circle will be R plus 3X, right? That is something that I immediately think of. The radius relationship between the 3 or 4 concentric circles must be in AP here. What else? Of course, there are areas. There are different places as areas that we can find out, not just circles areas, but also area of the part between the circles, area of the first red strip, area of the first white strip, area of the second red strip. All of these you can calculate. What else? Very, very important thing that several people miss out is that if I join the concave vertices of this pentagram, I will get a regular pentagon. So there is a regular polygon which is hidden inside this figure. So regular polygon or regular pentagon properties, right? Some of the interior angles of a pentagon, some of the exterior angles of the pentagon. Using that, not only can you figure out angles of this pentagon or area of this pentagon, you can also figure out that all of these triangles are isosceles triangles and their base angles will be equal to the exterior angles of this regular pentagon. So pentagon based properties you can apply, right? So that is how we need to start thinking about shapes and figures, not just while we are practicing questions, but in general life as well. And that will help you remember, say, properties better. That will also help you recollect the relevant concepts to a question inside the examination better. Right? Now let's do one thing. Let's solve a couple of questions. Okay. Although I'm not going to solve a question, and why I'm saying that I'm not going to solve a question is because my point or my aim is not to come up with the correct answer, but my aim is to help you develop a sense of understanding about the approach that is required to get to the solution of a question. Right? So the first question that I put here is going to be all about visualization. Right? This is the text of the question. I'm going to give you 30 seconds. You are going to read, understand, visualize, and in 30 seconds, you're going to draw the figure. And then I will show you the figure, how it looks like. Right? So that you can match whether whatever you visualize is the same figure that has been described in the question. Right? So read this. Okay, so that is 30 seconds up. Okay, so if you have visualized this properly, then the figure that you should be getting is this. This is X, it's not Y. If I just properly, this is X, this is Y, point of contact A. This is PQ, right? And this is BP, this is AB, this is BQ, AB and AP are all equal, right? And this is the figure that you should have drawn as soon as you read this question. And visualizing this should not take longer than 30 seconds. Now, why I picked up this question specifically is because I made this question in such a way that it is very confusing to visualize this without a figure. I'm not saying that such difficult and complicated visualizations will be present inside the CAT paper. Probably they would have given you a figure for this question in the actual examination. But this level of complexity, we should be able to tackle as far as visualization is concerned. Because in mensuration questions specifically, I've seen several times CAT throw up questions, which is all about being able to visualize how the end figure, which will give you the solution, is going to look like. Now, if you have drawn the figure correctly, say by reading that question, then give yourself a pat on the back. Now, you can look at this figure, do whatever kind of association you can with respect to what all concepts do you think can be applied to this question. Look at what's been given, look at what's been asked. I will again show you what's been asked here. We have been asked to find out the length of AQ, right? Everything else what is given has been written inside the figure, so I have to find the length of AQ. So then you think and you associate. Again, I'll give you 30 seconds to think about what all concepts do you think can be applied. And then I will tell you how to arrive at the solution of this question. From here on, it's a pretty simple question to solve, right? Why? Because if you are doing the association part of it properly, you will immediately realize that the first thing that you have to apply in this question is the alternate segment theory. Right? The angle 60° that's been given, it's an angle between a chord and a tangent at the point of contact. So if this is 60, angle PBA will be 60. Also, in triangle ABP, we have been told that AB and AP are equal, which means it's at least an isosceles triangle, which means angle BPA will also be 60. And because we have been told that angle QPA is 120, which means that angle QPB will also be 60. Now, if I look at triangle ABP ends up being an equilateral triangle, right? So why? Because there are two angles which are 60, so this third angle should be 60° angle as well, right? Also, we can see that this angle here is 60, this angle here is 60, which means PQ and BA are parallel, and BP is a transverse. That's why PQ and BA are parallel lines. So there is also parallel line and transverse system in this figure. Right? What else? Now, if I look at triangle QBP, I have got BP should also be equal to BQ because triangle ABP is an equilateral triangle. So BP will be equal to AB will be equal to AP. And I know that AB and BP are equal to BQ. So which means that BP will be equal to BQ, which means BQ is also 6 centimeters. Now in triangle BQP, I have got BQ and BP equal. So it's at least an isosceles triangle, which means base angles must be equal. So this angle must also be 60° angle, which means the third angle again will be 60° angle, which means triangle BQP is also the same equilateral triangle as the one before. Which means what kind of quadrilateral is QPAB? QPAB is a rhombus. So QPAB is a rhombus, which means that the diagonals are going to intersect at right angles or bisect each other at right angles, which means that I've got right angle triangles. Which means all concepts associated with right angle triangles you can now apply. And that is what will help you get to the correct answer of this question. Right? I'm not going to tell you what the answer is. If you've calculated it, then that's great. You can leave it as a comment under this video and I'll tell you whether you're right or not. And I don't think you need my say confirmation here. But this is how association is going to help. Now, if I look at all these points, right, the 5 points that I've written here, the 5 different geometric concepts that can be applied to this figure. Of these, the last 4 are not even or were not even present in the figure to begin with. Only the first one was. And that is what is going to happen, right? In most cases, because initially, if you say, look at the figure, I will see a circumcircle, I will see a triangle, I will see tangent, I will probably see even a secant or a chord, and I can think of chord section theorem, and then tangents, I can say produce and make them meet at the same point, and then I can say that tangents from the same point to a circle are equal in length. All those concepts can flash across in our head. But what tells me that alternate segment theorem is the only concept which is relevant to this question is the given data. The given data is a 60-degree angle. Even though we have been asked to find out the length of a side, we have been given the length of a side BP, with which I can do nothing in the figure to begin with. But the 60-degree angle, which has been given as the angle between AP and XY, between a chord and the tangent at the point of contact, that will tell me that I will probably have to apply the alternate segment theorem. Even though the alternate segment theorem is an angle-based concept and has got nothing to do with side lengths. So the given data is going to show us the way that where are we supposed to think towards, and if this concept flashes across my head immediately, if I, as soon as I look at the given data, then I will be easily able to get to the correct answer of this question, right? Provided every step that I'm making subsequently from here, right? First, I'm applying alternate segment theorem, and then I'm looking at the result that I'm getting, and then I'm asking myself, oh, now which concept can I apply? So the next concept that I actually applied was that the sum of the three angles of a triangle is 180. Then I ask myself, what concept now? Then I can say that, oh, now I can apply equilateral triangle concepts. Also, next I looked at two angles which are equal. Now, what concept can I apply? I can apply parallel line and transit system concepts. So these concepts can only flash across your head when you keep on updating the figure in your head, and the figure then tells you what all geometric concepts can you now apply to the question. So this is what I mean by association between what is present in front of you and what all concepts are available for you to apply, right? So initially, probably the given data is going to tell you what geometric concept to apply. But after that, you have to keep on updating the figure, and the figure will keep on telling you then that subsequently what concepts are supposed to be applied to get to the answer of a question. Okay, so this is what I wanted to basically communicate with the first question. One more question we will solve before we end this video. Right? Now, this question, let me tell you from the very get-go, is not a CAT standard question. You will not come across such a question inside the CAT paper because it's pretty complex and it's pretty lengthy. If this question is present inside the CAT paper, then my advice is let it go. Do not solve it during the paper. This question is not supposed to be picked up. But I'm still going to give you about 2.5 minutes to look at this figure and think about all the concepts that you can apply to this figure, because this is a perfect example of a question where looking at what's been given, looking at what's been asked, and then thinking about the geometric concepts and applying them, how the figure modifies itself will tell you what all concepts more can you apply moving forward. Okay. So I'm going to give you 2.5 minutes. Think about this question. Try to solve the question. Even if you're not being able to arrive at the solution, make a list of all the concepts that you think can be applied to this figure. If you want to make constructions, make constructions. Then look at the constructions and then see, because of the constructions, if there is any more geometric concepts that you can apply, list them down. And then when I discuss a solution of this question, you can then match whether what concepts and theorems you had thought about were the same ones which are being applied inside this question solution of it. So take 2.5 minutes and think about this question. Okay, so that is 2.5 minutes. So if you have thought about this figure well enough, then you would have figured out that there are so many things that you can actually apply, so many concepts that you can apply to this particular figure. Right? Now, how will I go about solving this question? Right? I will look at what's been asked. I can see a right angle triangle, I can see a semicircle and a circle inscribed inside it. But I look at what's been asked, and I've been asked to find out the radius of the circle. Right? The small circle's radius I have to find out. Now, what we'll remember in geometry is that if I don't even have a path directly to the quantity that's been asked at the end of the question, then I can ask myself that can I at least get to some kind of an intermediate dimension which is present in this figure? Because that then can help me get to the final answer. For example, if I look at this figure, what are the dimensions which can definitely be helpful for me to calculate the value of the radius? Of course, if I have the length of AC as 5, if I can figure out what is the length of AD, what is the length of DF, what is the length of FC, that is going to help me. Similarly, BC is 4, which means if I can also figure out what is the length of BO, OE, and EC, that can help me. Right? Also, what else can help me? We have not been asked to find out the radius of the semicircle, but I can tell that that is also a dimension which is present inside this figure, which can contribute to the solution of this question. So although I've been asked to find out radius of the circle, I can also, it will definitely help me if I can find out the radius of the semicircle as well. Okay? So these things are clear to me inside the head, that more dimensions that I can figure out inside the figure of a geometry question, the more data I can actually get out of that particular question, or calculate in that particular question. Right? So that is my first thing. Second thing, I have to ask myself that in this figure, can I make certain constructions which are very common constructions which I can instinctively think of? And I think all of you will agree that there are tangents in this question. Right? AB is a tangent to the semicircle, AC is a tangent to the semicircle and the circle, BC is a tangent to the circle. So many tangents are there. So whenever I see a tangent, I will of course draw normal. So it's the first thing I'm going to do. Right? I'm going to draw the normals in the figure. First, I'm going to start with a semicircle. Right? For some reason, I find dealing with the normals of the semicircle to be slightly easier. And I'll tell you why. Why? Because there is more data with respect to the normals of this semicircle, because I know the length of AB. I know the length of the tangent here. I do not know the length of any of the tangent of the circle, but I know the length of the tangent of the semicircle. AB is 3. Right. Now, one more thing that you should have realized if you have solved about 100 questions of the easy and medium level questions of geometry is that whenever two tangents are tangent to a circle from the same point, then the length of those two tangents are equal. Right? So which means if AB is 3, then AD is also 3. Right? So which means BC will be 2. Right? If I write this BC here, BC of course will be 2. What else? One more thing we have to remember, that whenever two tangents are drawn to a circle from the same point, then if I join the center of that circle with the point of contact of the, not the point of contact, the point in common to the two tangents, right? Then this straight line will divide the resultant quadrilateral into two congruent triangles. These two triangles are definitely congruent, and this is a very common figure inside geometry that you'll find, that there are two tangents from a point to a circle. And if I join the center to the meeting point of the two tangents, then I get two congruent triangles. How? Simple SSS congruency. Length of the two tangents are equal. This side AO is common to both. OB is also radius of the semicircle. OD is also radius of the semicircle. What this implies is that angle BAO and angle DAO are equal. These two angles will be equal to each other. Now, this is where updating our visual capability of looking at what all different geometric features are present inside the figure should tell us what concept can I apply. See, at the end of the day, I'm trying to calculate lengths here. So I'm very happy to apply concepts which deal with side lengths. And now if I look at this figure and I look at the fact that AO is bisecting angle BAD, which is also angle BAC, then I will know that AO is an interior angle bisector of triangle ABC, which means I can apply the interior angle bisector theorem. And interior angle bisector theorem states that, or if I apply that here, I'll get AB by AC is equal to BO by OC. So why am I applying this? Because remember what we had said, that any dimension, if I can find out in this figure, then I can, then that can help me get to the radius of the circle better. Now in this ratio, I know AB. I know AC. I don't know BO, but BO is radius of the semicircle, which I can take as capital R. And OC, then I can take as capital R, or rather, sorry, it's slightly mistaken. Change that. I can take OC as 4 minus capital R, which means now in this equation, I can simplify this and I can find out the radius of the semicircle, which is a big win for me. I have found out the radius of the semicircle. I have found out the length of OC as well as a result, right? So I know OB. I'm not very sure what is the length of OB, and I don't care because, as I said, I'm not worried about the solution of this question. That you can solve very easily. I'm going to talk about the thought process, which is required to get to the answer of this question. Right? I have OB, I have OC. Right? So radius of the semicircle is there with me, which makes me very happy. Right? Now, next, after this, what do I do? What can I do to get to the radius of the circle? So what you can do, of course, is that the same constructions that I made for the semicircle can be made for the circle as well, because the circle will also have normals to the tangent. The circle will also have a straight line joining the center to the meeting point of the two tangents. So let us draw that and let us see what we get out of that. So out of that, I get this figure. Right? Now, if you see closely, a very important thing that I've constructed here is that I have taken the straight line, which is joining the meeting point of the tangents with the center, and produced it to meet OD. Now, why did I do this? Right? If you have an idea as to why I have done this, then you are very good at geometry and you've gotten very good at associating what's been given with what has been asked. Right? Why I have produced it to CQ, or say CP to Q, is because in this quadrilateral FPEC right now, we do not have any of the dimensions. That's why I produced it to a straight line for which I know the dimension of, because I know that OD is the radius of the bigger circle, right? Or the semicircle. Right? So that's why I did this. That is one reason, of course. Another reason is what? Another reason is that I know that a normal is always perpendicular to the tangent at the point of contact, right? And I also know the length of DC. That's why I produce CP to Q. Why? Because now you should be able to look at this figure and then understand what geometric concept can be applied to this part of the figure. And the concept that I'm talking about is the concept of similar triangles. Definitely, OD and PF are parallel to each other, which means you can apply similar triangles concept here. Right? Also, what else can you apply? Once again, when I produce CP to Q, then once again, this angle is going to get bisected. Angle C is going to get bisected. So which means that CQ is an interior angle bisector of triangle OCD. So I can once again apply the interior angle bisector theorem. Both of these will give me different ratios. And the fact is that I'm going to leave this again up to you to apply the similar triangles concept and the interior angle bisector theorem concept. I'll tell you first apply interior angle bisector theorem, then apply similar triangles concept. If you take the radius of the circle as small r, then what you will be able to do by applying these two is that you will be able to find out the length of CF in terms of small r. Now, why is that important? To find out the length of CF as a function of small r is important because this is also equal to CE. So I will get two more dimensions which can definitely help me get to the answer of this question. I can find out FC and EC. But now the question arises that how are FC and EC going to help me find out small r? How are they going to help me find out small r? That is again a concept that you should have thought about as soon as you looked at the figure and as soon as you looked at what has been asked. What was asked here? I was asked to find out radius of the smaller circle. In this figure, which geometry concept in the basics of geometric videos that you remember that I had discussed is somewhat associated or has present inside it radius of the smaller circle? That concept is very simple. To remember that concept, we only have to realize that the semicircle and the circle are touching each other at exactly one point. And we had discussed in the basics of geometry class, and anyone who has a very basic understanding of the theories and theorems of geometry, of circles especially, will realize that whenever two circles are touching each other at a point, then the distance between their centers will be equal to the sum of the radii when they are touching each other externally, or will be equal to difference between the radii when they are touching each other internally. So that is the concept that I'm going to finally apply to get to the answer of this question. How am I going to do that? Because now if I look at the straight line OP, OP will be capital R plus small r, in which I know the value of capital R. EP is small r, and OE, this length OE, will be OC minus CE, which is a function of small r. Length of OC we already know because it will be 4 minus the radius of the semicircle, right? So now I have got three sides of triangle OP, which is a right angle triangle, all in terms of small r. And right angle triangle means now you can apply the Pythagoras theorem. So you can apply the Pythagoras theorem, solve for the value of small r, and that will give you the correct answer. I don't know what the answer of this question is. I will calculate it a bit later, but this is how you reach the answer of this question, right? Now, if you think about how we thought about the solution of this question, you will then realize the importance of association. The first thing that I could associate is the figure. The figure told me that there are tangents, so I drew the normals, right? Second thing that I could associate is that as soon as I draw the normals, I realize that I've got two tangents from the same point for the semicircle, which means that I can have two congruent triangles. Two congruent triangles means that two angles will be equal. Then that led me to associate two angles being equal with interior angle bisector theorem, because that can help me transit from dealing with concepts based on angles to dealing with concepts based on lengths of sides. And I'm trying to find a length in this question. So I applied interior angle bisector theorem. I found out radius of the semicircle. Then I thought, why not apply the same concepts to the circle? That's why I made the normal construction in the circle. That's why I made the straight line joining the center to the meeting point of the tangents. And that's when I realized that when I do this, I get normal of the semicircle and normal of the circle to be parallel to each other. Those two parallel lines then told me that probably I can apply similar triangles concept, and that's why I produced CP to meet OD at the point Q. And then similar triangles I had figured out. Interior angle bisector theorem I had just applied, which means I can apply that again. And then once I had applied that, then finally what has been asked inside the question, the radius of the circle had told me to think about that particular concept, to associate the solution of this question to that particular concept, that distance between the centers of two circles which are touching each other externally will be equal to the sum of the radii. So I applied that concept and I finally came to the correct answer. Every concept that you can associate, if it is relevant to what's been given and what's been asked, even if it is not relevant to what's been given and what's been asked, even if it's just relevant to the figure, apply it and see where does it lead you to. As soon as it leads you to some place, ask yourself that this new data will help me apply which concept, and this new data will help me apply which concept. Right? In the meanwhile, whenever you think of a new concept that can be applied inside a geometry question, ask yourself, that is the concept that I'm applying relevant to what's been asked? Is it relevant to what's been given? And then pick and choose the particular concepts which are relevant to the data which is given and the data which has been asked. And slowly and steadily, any question of geometry you can solve like this. This is how we think about geometry questions. And for this, of course, we need to have a proper knowledge of all the theories and concepts of geometry, which requires extensive practice, of course. And also it requires extensive practice to even slowly and steadily start to develop this particular association. In the meanwhile, do not forget to look at any geometric shape in your day-to-day life and start associating concepts and theorems that you've studied with them. That will help you a lot in the examination. All right, guys. So that is basically what I wanted to communicate in today's video. So thank you everyone for coming and have a good night. Take care.